So this is a video of how to convert Cartesian coordinates into polar coordinates in the grid. Maybe that means nothing to you, maybe you don't really care about what that means. Let me just quickly tell you what it's useful for. So essentially every time you want to make kind of a spatial panner kind of thing, you probably want to convert from Cartesian to polar coordinates. So let's say we've got this XY controller and we want to imagine that this in the middle here is a person. And then we've got this coordinate system, I've set these both to bipolar, where this kind of moves around in a space. So this is a sound source and we're this person in the middle. So two things we're really interested in are, one, how far is this object away from us? And B, what is kind of the angle of this object? So if we're looking here, is it here? Is it somewhere here? Is it somewhere here? And the way we can do that is by using polar coordinates. So if you've done a bit more physics or engineering or something, you've no doubt heard of this. If not, that's no problem. I'll just walk you through the process of what we're gonna do here. So once again, we've got this these two coordinates. We've got this r here, which is the distance from our coordinate origin, and we've got this phi here, which is kind of the angle of this. And we can kind of use these formulas to calculate these from just having our x coordinate and a y coordinate, which is what we call Cartesian coordinates. So let's first calculate the distance, because that's still relatively simple. So basically we just need Pythagoras. A squared plus b squared is c squared, because we've got our a squared here, which is the x, we've got our b squared here, which is the y, and then to calculate the distance we need c squared, which is the line directly to the point. So what I'm gonna do is I'm just gonna get exponents, get an a squared and get a b squared. I think blue is our y and red is our x. And then you can see we can add these together. And because we want c and not c squared, we need to take the square root of them. And so if we've got the scope here, we can see this kind of outputs now the distance of a dot from us. So if this is at 0, this distance here is 0. And once we move this up, kind of move around in circles around it, it stays the same. And if we go further away, the highest value is in these corners here. Maybe we need to set the scope range to a bit higher than 1. Because you can see in these corners here it is exactly at 1, and then here it goes a bit up. And this is kind of a distance for our little sound source here. Then another thing we want is our angle. So what we can do for this is we can either use this weird arctang formula, which I think is a big pain in the ass, or because we've already calculated our r, which is our distance, we can just use this simple formula, arc cosine of x over r. So we don't really get an arc cosine in the grid, which is a problem. But if you know a bit more about physics or maths, you know that you can kind of approximate this function by a polynomial using a Taylor series. So what I did here is I just input arc cosine Taylor series expansion at x equals 0. So basically what we want to do is we want to create this, because this is something that we can recreate with grid modules. Now, this isn't going to be precise, but for most values this is going to be pretty good, which is kind of, if you're a mathematician you won't like this, if you're a physicist or engineer you won't care, this is perfect. So let's get, first of all, let's get our pi over 2. So what we do for that is we just get a constant, and I'm gonna do another awful thing here that will make some people very sad and some people won't care at all. I'm gonna say that pi is just 3.14 because I don't really care for exact values here. And then 3.14 over 2, let me quickly think, that's like 3.14. I'm sorry, I'm a bit stupid, so I'm just gonna use this calculator for it. 3.14 over 2 to keep this video moving. My internet is very slow right now. Yes, I could just use my local calculator, whatever. 3.14, 1.75. So that's nice. That's our pi. We're gonna delete this later anyway, so you'll see why. 3.14 over 2, 1.57, I think, was it? Yeah. I'm unfortunately very bad at mental arithmetic. So yeah, 1.57. Then what we need to get next is this term, we need to subtract x from it. So we need some kind of, let me go here. In this case, because we're doing this coordinate transform, our x is x, so our x coordinate over r. So what we need to do is here, we need to divide, and then we get the red thing, which is the x coordinate, and our value for r here. And then we need to subtract this. So subtract this x coordinate over r from our pi over 2. Now next thing, we need to also subtract x times x times x over 6. So let's just do that. Exponents get cubed. Divide that by a constant, in this case 6, and then subtract that from this here. Nice. So let's look at the next term. I think we'll do this, although probably this isn't even really necessary. X to 5, 3 times x to 5 over 40. So let's just get another exponent here. Once again, this x over r is our x. This is gonna be a big mess. I can already see that. So 5 multiplied by 3 and divided by 40. So get multiply this by 3, divide this by 40, and then once again subtract this from, no, subtract this from our term. And now basically we need to do this once. But you can see if y is smaller, if y is bigger than 0, this is going to be positive, and then if y is smaller than 0, we need to multiply this by -1. So what we need to do is we get like a choose bigger than. If y is bigger or equal to 0. So get a blue Y wire here. Get a constant, which is 0. What we need, this is positive, I think. And if y is smaller than 0, this is negative. So what we need to do is we get like I always forget what these things are called. They're like logic modules, I think. They're like choosers, you know, that kind of mixing or something, I think. Select in. So if this is bigger than 0, this is fine. We select. This is gonna, let me quickly see how this select in works. So I'll just input this button. So if I press this button, it selects the second one. So if this is true, I wanted to select the second one, which is gonna be our positive value. And this, if this is not true, I wanted to invert this. Show help. So multiplies by -1, invert this thing's polarity here. I wanted to choose that. And so now what we've got here for this function should be our phi. Now, let's see. Yes, that's nice. Okay. You can see how it kind of goes down to 0 here. And it's not very precise, especially around this here, but I think we can live with that, to be honest. And then we can kind of go around here. And once again, because it's like a circle, it just flips over. Now, ideally, what I would want this to be is I would want this to be negative when it's in front of us. 0 when it's in front of us. So I think if I just set this to 0, yep, because as you can see with these polar coordinates here, this is all relative to the x-axis. And if it's at the y-axis, it's exactly pi over 2. So I want this to be 0. So I am just gonna subtract pi over 2 by removing this pi over 2 at the start. And now what I've got is, I've got like this wonderful little angle here that can kind of give me how much this is panned by. And then I've got this lovely distance function here, which tells me how far this point is away from me. I should probably turn this another color so you can actually see what it does. So yeah, blue is the distance. And then red is the panning. So to the left, to the right. Now, if you want to convert this further, you would kind of make sure that this angle is the same for front and back and stuff, and you would try to map this thing to panning somehow, and this distance here maybe to volume, and drop off some high frequencies, maybe implement some crossfeed, all that paleo kind of stuff, maybe build your own little pinner filter or whatever. All that stuff maybe is for another video. I just wanted to talk in this video about basically how to use the Pythagoras theorem and then the arc of cosine and its Taylor series to kind of get this in the grid. I guess the core of this video really is, yes, you don't get arc cosine, but you can just do the Taylor series of it. If you know about Taylor series, maybe you didn't think of that before. If you didn't know about Taylor series, basically any continuous function can kind of be approximated by a polynomial. So if you ever need some other function in the grid, you can just try to use its Taylor series, and it's like a very physicist-y kind of solution to everything. Just do a Taylor series, it'll be fine. So yeah. I don't know what kind of person would care for this or get a kick out of this, but I felt like I wanted to make this video, so now I did it. Hope you enjoyed. Hope you maybe you find some cool uses for this. I'd be really curious to see it. So yeah, see you in the next one with something a bit more practical and reasonable and less unnecessary, maybe. Probably not, you know me. It's probably gonna be pretty unnecessary, but still kind of interesting maybe. So yeah, see you.